my name is Jana, and together with my colleagues, I made a statistical approach for preload monitoring of balls to drive. So first of all, as maybe not everybody knows, I want to explain what a ball screw drive is. So it's very similar to a ball bearing, but it's a linear movement, and you have like the balls going on a spin wheel. So one possible fault in ball screw drives is preload use, which comes into the picture if we have aggressive wear of the foot contact. And this is very important to detect this early because it has a high influence on the quality of the manufactured work pieces. So next point is what is preload? Maybe also not everybody knows that here. So if you just saw the ball screw drive, and the preload is when it's manufactured, there's always a force between the balls and the ball screw, even if the ball screw drive is not moving. And then from time to time, when there is wear, the preload got lost and you got backlash or even more backlash. So first I want to introduce some state-of-the-art sensors which are used for the ball screw drive monitoring, even though my paper is on the algorithmic side, but to make it more understandable. So there are indirect measurements of the load, which are usually done by acceleration data. The advantage of this is you can easily retrofit it, and acceleration data is studied quite well in other applications. There's also a disadvantage. There you have to install an external sensor, but not fit into it, and it's very has some problems with external distributions. Then there is another indirect measurement of the load with the internal motor control data. This is very easy because you don't need to make extra measurements. But the disadvantage is when you see it in the control data, it's already very late and there's maybe already too much wear. Then there are direct sensors where you can directly measure the load. They are usually integrated in the nut, and it can be spring direct or piezoelectric sensors. The advantage is you can directly measure the load and you can by that early detect somewhere. The disadvantage is it's very complicated to integrate it into the nut because it still has to be stable and run. So my paper is with that sensors which are integrated in the nut. And as I said, it's on the algorithmic side. So I shortly want to give the state-of-the-art applications for evaluation the data of sensors integrated in the nut. In the first application, they use piezo-resistive thin layer sensors and could in general show that there is a relationship between the mass of resistance and the preload force. In the second publication, they use piezo-resistive thin film sensors again, and additionally strain gauge sensors, which they could also just in the raw data see that the mean is decreasing while they were executing the tests. In the third publication, they use strain gauge sensors again, and they had an algorithm which they just have a sliding window over the raw data, and then they took the maximum amplitude and associated that with the preload, which is already our algorithm, but it has a disadvantage and it's very sensitive to outliers, as you can imagine, if you just take the maximum amplitude, and it's also a problem with noisy measurements. And on that problem, we want to work with and propose an algorithm. So first of all, the experiment setup. As I said, we have the sensor integrated in the nut. It's very easy to see here, the nut and the ball screw. And as I said, there is always a force between the balls and the ball screw, and this force or pressure is directly measured here with the strain gauge sensor. For the data, we executed different experiments. So it's very common to simulate wear for ball screw drives by using different ball sizes, because ball screw drive usually wear out over years, so over 10 years, and nobody wants to wait 10 years. So we have the biggest ball with the optimal preload, and then for a smaller ball already a preload use and beginning backlash, and then the smallest balls have backlash and even strong backlash. The data was recorded with 3 different rotational speeds, 1000 RPM, 1500, and 2000 RPMs, and we're just driving the ball screw drive back and forward, so just to get a signal. So the algorithm we proposed is a statistical method to characterize the ball's motion. And in the end, we define the health value so that you have an indicator for the accuracy. So first of all, we took the data, and the question is, can you see the error in the data? So on the left side, we have data with preload, and on the right side, we have without preload. And yeah, it looks different. And we figured out that if there is preload, the balls are moving very smooth. So every has the same rotational speed, and it's just going very smooth. If there is no preload anymore, they kind of got stuck. And some of them are faster, some of them are slower, and then you got some gaps, and you see that the balls are just moving more irregularly. And this is something we wanted to take as motivation to find a statistical approach which kind of measures this irregularity of the movement. So in our approach, we have a few different steps. So first, we have the raw data, so with a sliding window over it. And one crucial thing is to detect if the machine is standing still, because if you would take that data into account, it would just polite the statistics. So if the machine is in operation, we just go on and execute some more steps over that window. We first have a low-pass filter, then we measure the distances between these extrema. Then we take the standard deviation of these distances. I will just explain a little more. And then we do all those steps in a sliding window over the whole data. And in the end, for better understanding, we define a health value, which is the mean of the distribution of the standard deviations. So yeah, I said it's crucial to know if the machine is moving or not. So we took the frequency spectrum of the Bose group of the data, and you can here see that in operation there is a peak, and in Stillstand the data is distributed randomly. So we exploit that to see if Stillstand or not, and we take the ratio between the mean and the maximum value of the spectrum to just see if it's standing still. Then the second steps, if the Bose group drive is in operation, as I said, we apply a low-pass filter, and the cut frequency here is just the highest peak in the spectrum, as you saw in the slide before. And then we have the minima and maximum, for just getting the distances between them. And then over every window, we take the standard deviation of these distances to have kind of a measure of how regular the balls move. So yeah, then I will just show the results in the evaluation. Yeah, as I said, we took data from that 4 ball sizes. So like the biggest ball size is with preload, and the smallest ball size is like very strong backlash. And here you can see an histogram over the standard deviation of the distance between the experiment. And it can be clearly seen that like the highest peak or the center of the distribution is at smaller standard deviations when you have the preload, and in higher standard deviations if you have backlash or even strong backlash. And you can see if with preload it goes deep down, and for backlash it's really like a wider distribution. And then now to define that into a more intuitive value, we define the health value, which is defined by 1 divided by 1 plus the distribution associated with the optimal load and minus the current distribution. Why we defined it like that is we wanted to have a value between 0 and 1, so that you have a healthy Bose group drive and it's 1, and it's going down when there is 0. So here are the results. You can see that if you have optimal preload, it's 1, it's defined like that, and it goes down. If you have backlash, or if the Bose group drive is worked out. And as I said before, the other algorithm has problems with outlier, and we just wanted to show that our algorithm is robust against outliers. So actually, this was a data set where we never really had an outlier. So we made once the algorithm with outliers, and the result are the 2 points. And then I just manually deleted the outlier, and we did it again, and you can see that the values are almost the same. So to sum up, we showed that there is a dependency between the smoothness of the ball's motion and the preload condition. And we proposed a statistical method to factorize this force motion and showed that this is robust for outliers. And in the end, we defined a health value to give it a more intuitive understanding, which indicates how the average varies and how the preload condition is. For future work, we want to generalize the algorithm for different rotational speed trajectories, because, as I said, we just were driving the force group back and forward. But yeah, optimally, it could just be used in operation of the force group drive, and then it have to deal with different rotational speed trajectories. This would also then include that the algorithm have to deal with accelerations, because they naturally occur in operation, and we need to adjust the algorithm for that. Thank you for your attention.